Okay, so now I would request Professor Mainak Poddar. First of all, I will introduce him. So, Professor Mainak Poddar, he obtained from his PhD from Wisconsin-Madison, and he held postdoctoral positions at Michigan State and the University of Waterloo. He was a faculty at IISER Kolkata, the University that Los Andes, and Metu NCC before joining IISER Pune. His main areas of interest are differential geometry and complex algebraic geometry. Currently, he is chair of mathematics at IISER Pune. He will today give his talk on polytopes, lattice points, and geometry. No. So I request him to share the screen and start the talk. Professor Poddar.
Thank you very much, Professor Katre. It's a great pleasure to speak on this occasion. So the birthday celebration of such an towering and inspiring a figure in Indian mathematics. And I thank you and the Bhaskaracharya Pratishthan for inviting me to give this talk. I'll just start by sharing my screen. So there we go. I hope it is visible to everyone.
Yes.
Okay. So once again, my talk is very elementary. It's mainly aimed at students, and probably there won't be much anything surprising for the experts. But I think the mathematics involved is quite beautiful. So although it is elementary, I mean, I won't be able to kind of go into the deeper aspects of it. I'll mostly focus on describing it from describing the the very rough outline. So I'll talk about polytopes, lattice points, and connection with geometry. And so in some sense, I mentioned in my abstract both algebraic and symplectic geometry, but mostly probably I won't have much time to talk about symplectic geometry. So, but the main thing is that, this will give us a connection between geometry and combinatorics. And this area is growing and growing, and it's huge, and there are many, fascinating results all the time, and so on. But what I'll focus on is something very classical from the, 70s and 80s. Anyway, so that's basically where this kind of subject started almost. So let us look at what a polytope is. So a polytope is the convex hull of a finite set of points in a vector space. So I'll just think of the vector space as real vector space Rn. And so it is the biggest convex set containing a finite set of points. So examples could be like simplices, for instance, the square in the two plane, etc., cubes, and so on. Now we are interested, for geometry, we are going to be interested in sort of a special kinds of polytopes with some restrictions. And what we do is if we fix a lattice that is like a free abelian group of rank n in Rn. So this is a copy of Z to the power n in Rn, and so we fix such a lattice, and we only consider polytopes whose vertices belong to that lattice. So if you are thinking of R2, you can think of like a square grid, and your vertices must be at the sort of another way to say, instead of the points on the grid, you can say integer vectors. So the vertices must be integer vectors. So such a polytope is naturally called integral polytope or lattice polytope. And in this talk, we will be only considering integral polytopes. So now, make some definitions. Now, if we have such a polytope, one of the interesting things is to count how many lattice points are in the polytope. So, and if I call my polytope P, I take this symbol, the hash mark P, to denote the cardinality of the intersection of P with the lattice M. Sorry. So, and also this, once I fix a lattice, I have a notion of a volume. So the unit cube or cell in the lattice will be will have volume 1. Okay, so we follow this convention. So okay, so there is this very old a formula from like 1899 regarding the counting of lattice points. So this number of points, integral points in P, in a polygon, so in a polytope in the 2-plane, and this is called Pix formula. And so here is an example. So look at this figure. So this is a red red 5-sided polygon, is an example of a lattice polytope. So you can see the vertices are all at the grid points. Now what the Pix formula says is that the number of lattice points in P equals area of P and plus half the perimeter of P plus 1. Okay, so one thing we'll notice is that although this is so there are some lattice points that belong to the edges, and there are some interior lattice points, and so together with vertices, these lattice points on the edges and the interior lattice points, we have the total number of lattice points. Now the area is kind of we can basically each square in the grid has area 1, so based on that we can calculate. When you look at perimeter, we have to be very careful. So perimeter, what is the length of an edge? So for an edge, I have to sort of consider something, the restriction of the lattice to the line of the edge. In other words, you can look at the lattice generator. So if E is an edge, you look at the sublattice, which is of M, which is generated by the intersection of the edge with M. So for instance, if you look at this edge E3, right, you have like if I look at extend this edge line E3, then you have this will have this lattice generated by these points. I hope you can, I'm not sure if you can see my cursor, but yeah, sorry about that. I haven't yet mastered my iPad. So, but anyways, I'm if you look at the E3, you can see 3 grid points here, and that generates a lattice. And with respect to this lattice, the length of E3 edge is 2. If you look at E4, the lattice, the sublattice is, coming from E4 intersection M. Over here is generated by this, like this vertex, the 2 vertices of E4. And with respect to that sublattice, the length of E4 is 1. So basically, when I consider, in general, when I consider volumes of faces of a polytope, I have to, restrict to the corresponding sublattice and take my volume element from that sublattice and compute it accordingly. But anyway, so let us this Pix formula has a combinatorial proof, which is, it's not like very simple either. And, but anyways, maybe several combinatorial proofs are available classically. However, we'll look at a sort of a generalization of this, and then we'll talk about a geometric proof. Now, let's verify this first of all. So if we count this number of lattice points here in this polytope P, count maybe from the top, and you go row by row. So 1 plus 2 plus 1, 2, 3, 4 plus again 4 and plus 2. So you can see you get 13 points. And area, you can divide it into some triangles and squares. And you can, well, anyways, I wrote down some calculation here. I divided into this green trapezium and 2 triangles. Anyways, and one calculates is 8.5, perimeter is 7, and so on. If we add up both sides, I have 1 plus 3.5 plus 8.5, which is equal to 13. Okay, so it's some of the things you can ask, okay, why half perimeter and exactly, so on. But so there is some mystery, right? That how exactly this is working and so on. One of the combinatorial strategies is to divide into triangles with lattice point vertices, and then prove some result about the area of a triangle that does not have any interior lattice point. That area one can prove is half, and then use like the Euler characteristic edge minus vertices plus edges minus that vertices minus edges plus face, that kind of is the Euler characteristic. So you can use, so the one strategy of proving this is of this type. Okay, but it's still quite a non-trivial theorem. And now we'll look at a generalization of this. This is due to Khovansky from 1977. And what he said is, if the number of lattice points in a polytope is equal to a summation of these R sigmas are some rational numbers, R sigma, volume P sigma, and sigma runs over the set of faces of P. So again, you can count the number of lattice points in P through some, now, yeah, so this kind of, I will explain how these R sigmas come about. The volumes I have already kind of mentioned what these are. Okay, so R sigmas would be sort of like, anyways, I'll come to them later. So now I want to, so this is kind of like a deep theorem, and solves a non-trivial problem. We'll get back to this theorem later. Now, what I want to do is talk about another very stunning theorem called the G Theorem. And the G Theorem is about sort of characterizing, sorry, I forgot to make it full screen. So the G Theorem is about characterizing polytopes. There are several versions. So I will look at one kind of polytope called a simple polytope. And simple polytope has the defining property that, so if it has dimension n, then at any vertex, there are exactly n codimension 1 faces. For example, like any polygon is simple, the cube is simple, but if you have a pyramid, in R3, that is not simple, because at the vertex of the pyramid, there will be 4 codimension 2 faces that will meet. Okay, so anyway, so now let us, so this G theorem is about, basically the number of faces of a simple polytope. And the thing is, we'll give some necessary and sufficient conditions on this number of faces that will, so we'll give, so suppose I have like a bunch of numbers, integers that are supposed to be, and the question is, can this be, can this vector with these integers be the face vector of a simple polytope? That is, does there exist a simple polytope with these numbers representing the number of faces of that polytope, of various faces of different dimensions of that polytope? Okay, so with that, let us look at this definitions, like Fi is defined to be the number of faces of a simple polytope P of dimension n. Fi is the number of faces of dimension n minus I minus 1. Okay, so this is done to make some formula appear easier in the sequel. And you set the f minus 1 to be 1. So if you put I equal to minus 1 here, you'll see is the number of face of dimension n, which is exactly 1. And yeah, as an example, f0 represents number of codimension 1 faces of P, and so on. Now, the theorem does not give the result directly in terms of these numbers Fi's, but it translates them into some other numbers called HI's. So these Fi's make up one vector called F vector of the polytope P, but we are going to talk about another vector called the H vector of P. And this H vector is determined in this way through this identity. And so H vector is, so you have given this H0 to Hn, you form this polynomial H0 t to the n plus etc. up to Hn t to the 0. And then you rewrite this as t minus 1 to the n plus f0 t minus 1 to the n minus 1, etc. plus up to fn minus 1. Okay, so from this identity, I mean, you can easily see that H0 is 1, the coefficient of Tn, and etc. So one can determine, and here is a formula which looks with binomial coefficients and slightly complicated. Okay, now actually the reason why these HPs are kind of, I mean, anyways, this is not, in the end, these HPs will have geometric significance, okay, and the theorem is called a G theorem because there is another vector called G built out of the H. So G naught is 1 and Gi is Hi minus 1. Anyways, I will not use this G vector as such when I state the theorem, but it's kind of, I mean, I just wanted to say, you'll see how it is involved, but yeah, also I wanted to, connect to the name G theorem, okay? Now, what the theorem says is that an integral vector f is the f vector of a simple polytope if and only if the vector satisfies the following conditions. First of all, Hi equals Hn minus I. This, for all I, this is called the Den-Somerville identity. And this proof was given in the 1920s for this part. Then we have this condition that H0 less equal to H1, etc., less equal to H. This is the box of n over 2, so the largest integer less equal to n over 2. So these H's are sort of, I go up to the middle, and there it is non-decreasing. And third condition is H0 is 1 that we already observed. And this difference is, they're non-decreasing, so these differences are non-negative, Hi plus 1 minus Hi, up to the middle. But there is an estimate here of Hi plus 1 minus Hi in terms of Hi minus Hi minus 1. And this estimate, I'll avoid, I have the next slide describing what this quantity is, but probably for conceptual reasons, it's not that important. So at the moment, I will skip it. If at the end anybody is interested, I can display that slide. Okay, so basically, so you have a bunch of such complicated conditions as such, and this, if you have a polytope, the H vector satisfies this, and if you have some vector H vector that satisfies this, then you also have a simple polytope. So that is the theorem. Now the theorem was proved in 1980. The necessity part was proved by Stanley using geometric methods, and the sufficiency part was proved by Bilera and I forgot the other name. Sorry, it's somewhere. I think in the previous page, Bilera and Lee. So they proved the sufficiency part in a combinatorial way. So anyways, this is one, this theorem was really created a sort of a sensation. I think it was conjectured by Macmillan sometime in the 60s, and then in 80s, when there were some new geometric methods developed, then Stanley managed to prove it. Okay, so here is this slide I'm skipping, and yeah, please, if at any point you have a question, you can stop me and ask. So far, we have just done like some combinatorial examples. Now, let us talk about the basics, the strategy, the geometric strategy for proving these theorems. But anyways, I think, at least for the G theorem, now there are purely combinatorial proofs. But anyways, the geometry, the connection with geometry is anyways very beautiful and enlightening. So let us look. So the main strategy is to associate to any integral or lattice polytope a geometric space, which is called a projective variety, and also another geometric object on that space called an ample line bundle. Now, a projective variety is basically a subspace of the projective space Pn, and I will actually define these things, although many of you would be familiar with this, but still I will define all these concepts. And now once you have this XP, you have the geometry of XP, and you can translate these combinatorial questions or statements into geometric statements about XP. Okay, and the G theorem follows from Hodge theory. So anyways, that's about some cohomology, some structure on the cohomology ring of XP when you have certain additional geometric object called for example, like an ample line bundle, or a Kähler metric. In that case, we have some decomposition of the cohomology, and also something, some more properties of the cohomology which are not available always. And so in Hodge theory, there is a theorem called the hard Lefschetz theorem, and one needs to apply that. And again, I will explain this towards the end, what this means and so on. And so basically, I mean, maybe, since I have already talked about cohomology, these numbers H0, H1, etc. This will be the, the dimension of the cohomology spaces. And hard Lefschetz will explain why this is non-decreasing. But this final condition 3 I showed in the bound or the estimate of hi plus 1 in terms of hi plus 1 minus hi in terms of hi minus hi minus 1. That is that is very special, and that bound is obtained by a theorem of Macaulay on graded commutative algebras generated by degree 2 elements. And it turns out that this cohomology ring of XP is generated by degree 2 elements. So this Macaulay's theorem can be applied. And so on. So I have used a lot of names and so on. So, but at least I want to give you like some basic idea of the type of objects or geometric constructions that are involved. And before I do that, just a remark that the generalized Pix formula due to Khovansky is obtained by applying the Hirzebruch-Riemann-Roch theorem to that bundle, special line bundle that I'm talking about, the ample line bundle that comes from the Polytope. Okay. So again, this is a deep theorem in geometry. So anyway, so these theorems would not be so easy to explain, but anyways, we will take them for granted, and we'll look at the basic actors in the play, the projective varieties and the line bundles, and we'll also look at something called sections of the line bundles, and we'll try to get some, some idea about why these are sort of probably captured the geometry. So construction of this geometric projective variety from the Polytope. Okay, so we need to look at the algebraic torus, which is nothing but product of C star, where C star is the multiplicative group of non-zero complex numbers. So, and then you take Cartesian, the direct product of several copies of C star, and that's an algebraic group, and that's called, C star to the n is called Tn for simplicity. And if you look at the functions on this space, this is basically generated, by as a ring, polynomial ring in these symbols, TIs and TI inverses. Like if you look at, so this will be Laura polynomials, better word to say, the ring of Laura polynomials in the TIs. And if you just look at C star, that is C minus the origin, then the functions are generated by T and of course T inverse. And okay, so these are basically the algebraic functions that are of interest. Okay. On the torus, and some of these functions are special. They're called the characters, And so these functions of, these characters are the generators. So basically, in a Laura polynomial, you have like coefficient linear combinations of these characters, and the character is sort of like T1 to the M1, etc., Tn to the Mn, and these mi's are integers, and m this vector m1 to mn I can denote by m, and that is basically, you can identify this with an element of your lattice m. So remember, we fixed this lattice z to the n in Rn, and here you identify that lattice with with the characters of the character group of the torus. Okay, and this characters form a group because you can see chi of m times chi of m prime is chi of m plus m prime. So that has a group structure. But anyways, so now there is some connection between the torus and the projective space. So we'll come to that. So basically, the projective space is a compactification of the torus. So now let me just quickly review the definition of the n-dimensional complex projective space. Here, dimension is capital N, and one can think of this as the quotient of the complement of the origin in Cn plus 1, modulo and equivalence relation. The equivalence relation is that any vector in Cn plus 1 is equivalent to a non-zero complex scalar multiple of itself. So basically, all if I take if I have a fixed vector in Cn plus 1 and I take all non-zero complex multiples, I get a complex line. And you can also think of Pn as the moduli space or the parameter space of complex lines through the origin of in Cn plus 1. Okay, now easiest example is P1. Here you have basically Z0 and Z1, and it's kind of the equivalence class of Z0, Z1 is written with a square bracket and with colons instead of commas. That's like standard notation. And you can, so it's the set of all such Z0, Z1 that cannot be simultaneously, you cannot have the zero vector, so they cannot be both zeros. And you can break it up into two pieces, U0 as a union of U0 and U1. U0 is the piece where Z0 is not zero, and thereby the equivalence relation you can divide by Z0 or multiply by 1 over Z0, and you get this. So it's basically all, it's all determined by this ratio Z1 over Z0, and that's isomorphic to C. And U1, similarly, Z1 not equal to 0, another copy of C, and two copies of C there are, one can easily check. The intersection is, none of these Z0 or Z1 are 0. So basically, inside this C, any of these C's, you will have that, inside, if you look at one of these C's, inside that is the intersection, and there, this Z1 over Z0, this coordinate is non-zero. So it's basically C minus 0. So this is C star. Okay, so the intersection, either way you look at it, is a copy of the torus. Okay, so you can see P1 is a compactification of T1, and there are actually two points that you have to add. One is like C minus the origin you have to put back, and the other you have to put a point at infinity. And you can see in that way that P1 is actually diffeomorphic to the two-dimensional sphere. So anyways, this maybe I'm boring you a lot, but in case you have not seen it before, okay. So now, okay, so I have not still constructed my XP starting from the polytope. I have talked about torus, I have talked about projective space, Pn. Now, what I need to do is the following. I'll use these characters, okay? So given a polytope P, you see M, the lattice points in the are actually now correspond to characters of the torus. And so you choose a sufficiently large natural number K. So you kind of magnify the polytope. Sometimes you may not need to, sometimes you do. And so suppose I'll explain that later, but suppose I have magnified it and then I look at all lattice points in that magnification. And what I do is for each lattice point in that polytope, I have a character of the torus. And I use that to map the torus to Pn-1 using these characters. So each character is a function on the torus. And so this gives a map of the torus in Pn-1. There are n coordinates here. And now, then you take the closure of this mapping. Okay, now why do I need to magnify? Because I need to make sure that, for instance, not all of these coordinates has a common 0, for instance. That could happen if everybody is in, like, say, in the plane event, in the first orthant or something, then there may be like all have a common power of like some Ti, T1 or Ti's. And so to kind of rule that out, otherwise if all of them have a common 0, this map won't be well defined. And also we want to make sure that the map is injective and so on. So, but it is known that if you magnify it enough, you can always get enough of these character functions so that bad cases are ruled out. And so the closure of this image of the torus in Pn-1 is the projective variety XP. And I can quickly give you the example of the P1 itself, how I obtain it from a polytope in that manner. So P1, I have delta, the polytope of dimension 1 in R1 is this 0 and 1, just the unit interval. That's my polytope, and I have two characters. Chi0 is t to the 0 is 1, and chi1 is t to the 1 t. And I look at 1 dot t for all t in C star, and from what we have seen about P1, the closure of that. So this is a copy of torus T1 in P1, and the closure is the whole P1. So this is how I obtain P1, for instance, from a polytope. And so the line bundle in this case is, for this one, is called O1. And so what is a line bundle? A line bundle over XP is a locally trivial family of complex lines parametrized by XP. So for each point of XP, you have a complex line that is a copy of C, and they vary nicely, right? Like some holomorphically or, in a nice algebraic way. So that's what a line bundle is. And so basically a nice family of complex lines parametrized by your XP. And a line bundle over XP can be specified by this kind of data for every, so you take a cover, fix some cover open cover of XP, and you take for every intersection U alpha intersection U beta, you choose a function on that intersection, a complex valued a holomorphic function without any 0 on U alpha intersection U beta. It has to satisfy a few properties, but I'm coming to that. But a function without any 0 or pole on these intersections for every intersection. Now, of course, there are some conditions which I have written. G alpha alpha, like if you have U alpha intersection U alpha, you'll choose G alpha alpha to be 1. And in general, this is called for every alpha beta gamma, this cyclic product alpha beta beta gamma gamma alpha with G's is 1. Okay. Now the explanation is like this. What you have is locally. I said locally trivial family, and here locally trivial just means that on each U alpha the line bundle is just a product, is isomorphic to a product U alpha cross C or U beta cross C. And the point is globally, you see, you need there's some twisting. So you need to identify these local pieces, but they are not going to be identified. They're going to be identified through some pointwise using some isomorphism of C. So basically isomorphism, vector space isomorphism of C is multiplication by a non-zero scalar. And that is exactly given by these functions G beta alpha X, say, okay? So at X, this is what these functions are doing. And of course, you can see that, if I have 3 such identifications, so the beta alpha means you're kind of looking at the intersection inside U alpha and going towards U beta. And then for this twisting, how do I twist? That is given by beta alpha. So alpha to beta, that's how the notation goes. Okay. Now let us, okay, let me go to the, probably don't have a lot of time. So let me kind of go to the punchline a little bit. So what happens is that, if you think of holomorphic functions on projective space, or just say P1, by Liouville's theorem, you see, you need entire functions on C. C is inside P1, and those are just constants, because if you have holomorphic function on P1, because P1 is compact, it must be bounded just by continuity, and bounded function on C is constant. So there are not interesting holomorphic functions on P1. So what these line bundles are doing, and functions are actually, okay, they can be related to they are maps from the space to space cross C. So a function you can think of as a map from your base space to base space cross C, right? So what we are going to do, because there are not enough functions, interesting ones, we are, instead of looking at maps into U cross C or X cross C, instead of X cross C, I will use these twisted things. These are the line bundles. And there, what you will see is that there are a lot more such maps, holomorphic maps. So these are called the sections of the line bundle. And essentially, we'll again right away go to an example. And the more twisting you have, the more sections, in some sense, you can have. Okay, if you twist by let's look at the example. But essentially, you see, the role of functions will be taken over by, and of course, in general, you know that the functions in geometry, like functions have information about the space. in many, not just in geometry, but also like in analysis and so on. But yeah, here, basically in algebraic or complex geometry, we would be looking at sort of sections of various bundles, and they'll have information about the geometry. So let us go so again, so let us see that, this U, beta cross C, etc. There are natural projection maps to the base. And there is a natural projection map from the bundle to the base always. And a section of line bundle here is a map from the base to the line bundle, such that if you take the section and you project back to the base, you get the identity map on the base. Okay. So as I explained, this is the trivial bundle, and the section of trivial bundle are just the functions. Let us look at P1. And for P1, I have this G01 or G10. Let us focus on G10. And here, basically want to look at a function on U0 intersection U1, which I know is like a C star, which does not have a 0, and sorry, yeah, which does not have a 0. And the only choices are powers of t. Okay, on C star, powers of t won't have any zeros or poles, and those are my only choices. And this is how I'm going to twist, and these are going to give me the various algebraic bundles in P1. Now look at example like it's twist by t, for instance. Now, if on the first chart U0 you take the section 1, and under the identification under the twisting, like you identify what corresponding section you have on U1, you multiply by G10, you get t, and you see it's both, I mean, holomorphic on both U0 and U1. Okay, and again, you can also start with 1 over t on U0. Here I have U0, U1 here, and you can see if t is a coordinate, 1 over t is a coordinate on the other one. And so on U0, you can start with 1 over t, again you do, and you get multiply by this G10, you get 1. So what you have, and any linear combination of these is also a function. So instead of constants, you get like a 2-dimensional space of sections of this line bundle. And when I twist by t power 1, I call the bundle O1. Anyways, that's just a name. But if I had twisted by higher powers, positive powers of t, I would have a lot more sections. And actually, you can try other possibilities for S, and none of them will work. For example, if I try 1 over t squared, which is, hello, sorry. Okay, so please tell me how much time I have left.
Well, 5 minutes.
Okay, thank you.
Yeah.
So if I try it 1 over t squared and I apply G10, I get 1 over t, but 1 over t is not, t is the coordinate on U1. This copy of C, 1 over t has a pole, it's no longer holomorphic. So there is this boundedness of the sections. And this, if you look at t, this bundle U01, I'm considering I saw 2 generators of the sections. And these 2 generators actually correspond to the 2 lattice points of my polytope delta 1. And in general, so this is very nice. We come up from the polytope, we come up with some projective variety. I come up with some line bundle. Yeah. Sort of, I mean, you can see by following procedure, I can say what are the sections, holomorphic sections. So that will determine the line bundle. So those holomorphic sections are generated by the lattice points of my polytope, those characters. Okay, And here you see an example for P1. So this is the main thing. This is like the basic apparatus. So idea is that sort of line bundles, or more generally like vector bundles, will have information. Their sections will have information about the geometry and everything. I mean, basically, I have this polytope telling me about sections of, at least you saw one important line bundle, but various other line bundles also. If I go to the sort of like the faces of the polytope, from there I have more information about other line bundles and so on. So the polytope has a whole lot of information about the geometry. And okay, so I am kind of done with like the basic. I mean, next what I do is, for people who are familiar, it will make some sense. For people who have not heard this terminology, it may not make a lot of sense. But anyways, you can just quickly summarize by saying how this leads to the proof. So cohomology of XP, basically if I look at a codimension one face of the polytope, it gives me a subvariety of codimension 1 of XP. These subvarieties are called divisors, and their homology classes are if you look at the Poincare duals of their homology classes, they're in H second cohomology. And it is known that these cohomology classes generate the cohomology of P. And that's how Macaulay's theorem about, this graded ring being generated by degree 2 elements comes into play. This H vector, H little p, is just the dimension of the H2p, the cohomology group H2p of X. And hard Lefschetz kind of what it says is that H2IX, there is an injective map given by wedging with the first Chern class of this ample line bundle. And the first Chern class is basically, one easy way to say it is, you take a generic section of the line bundle, you look at the zero set of that, and you look at the homology of the zero set, and you look at the Poincare dual, and you get an element in H2, again cohomology. And so this map is injection up to the middle. So that's hard. That explains. So this, now if you just use these facts, you come. I mean, this is what Stanley did. He put all these facts together, and you have the necessity part of the G theorem. And finally, the counting of lattice points comes from this Hirzebruch-Riemann-Roch theorem, whose statement I write here. So the Euler characteristic of the space with respect to the line bundle L is given by some combination of some characteristic classes called Chern character and Todd character or class. And is whatever these are, what happens is that the Euler characteristic for these line bundles, these are generated by this ample. So for them, all these higher cohomologies vanish, and you only have to look at H0, which is basically dimension of that is counting the generators of sections, holomorphic sections of L. And that's exactly the number of lattice points of P. So left-hand side is the number of lattice points of P. And the right-hand side, I mean, let me just tell you that this Todd class is this combination R sigma, V sigma. V sigmas are some subvarieties again, and they are coming from these DIs, intersection of those divisors and so on in some way. But anyways, so this is how those R sigmas are obtained. Now, this theorem proof is still, even if you have this, Riemann-Roch formula, there's still a lot of work needs to be done to reach the conclusion. And, okay, I mean, some of it is very clever and interesting, but yeah, we do not have the scope in this lecture to go into that. So I'll stop here, but I'll give you some references and where, if you're interested, you can look this up. The first is this book, Introduction to Toric Varieties by Fulton. And so this is an algebraic approach. If you have a more topological mindset, there's this Bookstaver and Panob's notes, Torah sections and their applications in topology and combinatorics, published by AMS. So thank you very much for listening. Stop.
Yeah, thank you very much, Professor Mainak Poddar. Very nice talk, and also relation to Hirzebruch Riemann-Roch theorem of the topics under consideration, lattice points, etc. So thank you very much. And now, if there are one or two quick questions, they are most welcome in case you want to ask anything. Or it is